Welcome today to ECEN 215 Principles of Electrical Engineering. Today we're going to talk about series and parallel resistances and then lead into voltage and current dividers. So let's go ahead and get started on this. So the first thing here is just a review of Ohm's law. So Ohm's law is just simply the relationship between voltage, current, and resistance. And it's a linear relationship, and it's just governed by really one simple equation. I is equal to V over R, which you can rewrite as V times IR, or R is equal to V over I. In other words, the relationship is resistance in ohms is volts divided by the current. If you memorize and maintain this reference sheet here, this should set you up for the rest of the semester. And it's also important whenever there's a question regarding power, which power is in the units of watts, you need to maintain the concept that power is the voltage times the current. Or it can be written as I squared R, which is the square of the current times resistance. And you can get to that equation by just simply looking at V is equal to IR. And since power is voltage times current, then obviously it'd be I times IR, which is where you get the I squared from. And power is V squared over R. And again, if you're trying to get current, it is simply V over R, hence the V squared. I know I'm kind of covering on some fairly simplistic algebra here, but the reason I highlight that is that usually when it comes to the test, and I'm grading things, I catch simple errors where people forget to square the I, and I'll get an answer that is completely incorrect, and I have to take off a few points because you got the power wrong. I understand what you're trying to get at, but it's fundamental. The equation is I squared R, not IR or V over R. So please remember that you know these six little equations, as simple as they are, can trip you up. So you need to make sure you memorize them and understand them. So when it comes to the test, you can include all of these equations on your note sheet, and I'd highly recommend that until they become just totally memorized by you. So here is just a screen of what various resistors look like. In a live lecture, sometimes I've actually handed out resistors and stuff just so people can actually physically look at them. You'll see them in the lab video that we're going to do for the lab. Of course, in a live classroom setting, in a live lab, you would actually work with the resistors, so you get an actual feel for them. If you've ever looked at a piece of electronics equipment, you have probably seen these devices on the circuit board in various forms. So there are basically three main types of resistors, at least the way they look. There's the carbon resistor, which is similar to the bottom resistor there, that the surface mount resistors, but clearly the difference between the carbon resistor up in the upper left-hand corner here, this one right here, versus the surface mount is the physical size. The surface mount resistors are what is mostly common in almost all your electronics equipment of today. Your computers, your laptops, your smartphone, for instance. The resistors, honestly, there are some that are literally no bigger than the dot I just put on the screen. They are microscopic almost. And then you have things like these wire wound resistors here, and these are power resistors. These are very used heavily in like heater type elements, such as this right here, this top one here, where you're trying to dissipate a lot of power out of a circuit for various reasons. So these are the three main physical classes of resistors. So we kind of put a physical component to what we've been studying here. And of course, we represent the resistor schematically, as you've seen so far, as just kind of a zigzag line that represents the resistance R. So just as a review of the lecture we had the other day, the exact same slide out of lecture 2, just sort of kind of give a chance now that we've had a day to kind of dwell on that, a couple lecture days to dwell on that slide, just to kind of review. So here we have Ohm's law, and this is really just a practice in Ohm's law. We have a power supply that's 10 volts, and we have this resistor that is 5 ohms. And the question is what is the current? So we have this current I that's going to flow through here. So the question is, what is I? Well, we know that I is equal to V over R. That is our equation, which in this case is simply 10 volts divided by 5 ohms, which is equal to 2 amps. So that's how we get that. This slide kind of lays everything out using the KVL and KCL concept, but fundamentally that's what you're doing. If you've got a power supply, um, you're looking for the voltage that's across the resistance, VR, which is that, and that would be what this is, VR. And you simply get 10 volts over the 5 ohms. It gives you the current going through the resistance. Now, just to hammer home the concept we had also the other day, we have two types of power going on here. We have generation power or supplied power, and we have absorbing power. So let's ask this question. If I've got this power supply here and the current is leaving out of the positive terminal, this current is going this way, and it's entering the negative terminal and leaving the power terminal, or the positive terminal. Here, the current is going through the resistor like so. It's entering on the positive and leaving on the negative. So as we covered the other day, this is absorbing, or this is, excuse me, this is, see, I tripped myself up. This is supplying or generating, whereas this is absorbing. So it's just important to make sure you understand the difference between the two. All right, so let's delete some of this. So we will be having a live Q&A session. This is officially the Monday lecture. So the way I'm going to handle this class is, unless something strange happens, typically the lecture is always going to be dropped the lecture prior to the Q&A. So for instance, this lecture is lecture number 3. Officially it occurs on Monday, June 1st. So on Monday, June 1st, we're going to have a live Q&A in which I will go over this specific lecture. I'm going to drop lectures the lecture before. So this lecture, for instance, will be available Friday, May 29th, and you would be able to review the material at your time, whenever you can, over the next several days. And then on June 1st, if you've got specific questions regarding this lecture, we'll go over it. Of course, the live Q&A, if you've got questions still about lecture 1 and 2, we'll still go over it then. The Q&A is for your benefit. It is not required that you attend the Q&A. But this is your opportunity to ask me questions, to explain something. You don't understand some simple concept, that's fine. We'll go over it. If something's a little more complex for you, we'll go over it. I'll try to make sure I stay on top of that as best I can. If you have an email, or if I get a lot of emails on regarding homework problems, we'll go over it. I'm going to have specific lectures this semester in which I do deliberately a recorded version of a homework review, but also the Q&A is concerned for homework review. If you're stuck on a problem, we'll go over it. So now we're going to talk about a concept called series resistance. So now we have these resistors, and what if we put 3 of them in series? We have, in this case, we have a circuit with R1, 2, and 3, and they physically are wired together. So you've taken the terminals of the resistors and you've essentially twisted them together. You got R1 is tied to R2, which is then tied to R3, and you got the 2 ends, making up the end terminals. And so the question is, what do we end up with if we do this? So think about that for a minute. If we have R1, R2, and R3, what would happen if we combine them together? And I want to make an equivalent circuit. I want to combine them together. I want to turn this into one resistor. What do you think that is? I'll just give you just a moment to think about that before I show you. Okay, so the way this works is you end up with simply the sum of the 3 resistances. You end up with the equivalent resistance. We're replacing all 3 of these resistors are being replaced with this one resistor. And it's simply the sum of the 3 resistances. Conceptually, it makes sense. And so if I had R1 was 10 ohms, R2 was 5 ohms, and R3 was 5 ohms, then you would have 20 ohms total. And that's just simply the equation for doing series resistance. Now let's take a look at this one. Here we have parallel resistors. They are all connected to the same terminal. So they're all tied to the same node, if you will. All of this is on the positive node. All of this is on the negative node. They're just wired in parallel. So what do you think the answer to this would be? What would be the equivalent resistance here? Well, it is the 1 over the reciprocal. So you have 1 over R1 plus 1 over R2 plus 1 over R3. And honestly, this can go 1 over Rn. So it can go, if you have 50 parallel resistors, and you will have 51 overs of the resistance 1, 2, 3 to R over, R50. And that's exactly what it is. Fairly simple. So for two resistances in parallel, there's just this easy little formula to remember. And you can actually use this formula for actually combining, if you will, pairs of resistors. So if you have three, you can take two, use this equation, and then take that equivalent and then use it with a third. And you end up, you can just basically keep chaining these together in groups of two. So if you take the equation we just showed you a moment ago, you can actually work out this equation. Works out the same for two resistors. So you have R1 times R2. So in this case, we have just simply two resistors in parallel. We have R1 and R2, and this is the equivalent. So if we had, if we had 5 ohms and 10 ohms, we'd end up with 50 over 15, which works out to 3 1/3 ohms. So if you want to play with this, you can. This is good to have this equation memorized. I do, but of course I do this every day for a living and for the consulting work I do. So this is just sort of like off the top of my head. But this is, if of the equations to memorize in this class would be Ohm's law, power, and probably this equation right here. So for three or more resistances in parallel, it's just simply this formula here, which is what we just talked about. And we're about to practice a few of those. So here we have a resistance network, and the homework actually is going to be a lot of this kind of stuff. You're going to have different resistance network. It's going to ask you, please give us the equivalent resistance value of this network. And so this is more of a geometry question more than anything. So we're taking a look at this resistive circuit. And the first thing to do is how you boil the circuit down and make it an equivalent is to find all of the series resistors and add them up, and then all of the parallel resistances and do the parallel, so on and so forth. Then you can go back and forth between the two. So first, let's take a look at this circuit. We have a total of 4 resistors in the circuit. And they're in both configurations. We have some that are in series and we have some that are in parallel. So let's take a look at what we can do first. First, we note we have these two resistors that are in series, right? And then this whole chain right here on top of that is then in parallel. And then that will be in series with that. So there's kind of 3 parts to this problem, if you will. So let's take it one by one. Let's first start with the 5 and the 15 ohm. So since they're in series, we add them together and we end up with this circuit. And we end up with a 10 ohm. We kept that the same. The 20 ohm that is now in parallel with this new 20 ohm resistor that we got simply by combining these two together. So that was the first step. So now what are we going to do? Well, this step we're going to take and focus on this parallel. So if we did that simple formula we had a moment ago, now I immediately know this looking at this, what the answer is without even having to do really any math. Pretty much know it in my head. But just simply doing the math, we have a parallel resistance. We have 2, so we're going to use the the two resistor equation we just had a minute ago, which was the 20 ohms times the 20 ohms. So we end up with 400 over 40, which works out to 10 ohms. So now we have taken this parallel branch and we have turned into RQ2, which is 10 ohms. So now we have turned this first into the 20 ohms, and now we've taken both of this, if you will, has turned into this 10 ohm resistor. So there's one last step. Now we've got to combine this 10 ohms and this 10 ohm here. Well, we know from being the fact that this is a series circuit, just simply is 20 ohms, 10 plus 10. And that's it. That is the conclusion of the problem. We have now reduced this much more complicated circuit with 4 resistors into one resistor network problem. So now we have another circuit here. Here we have, again, 4 resistors. This time we have a 2 ohm that is in series with our 2, 3, and 4 that are all in parallel. So what do you think we should do first? Let's look at this. Well, I would probably start this simply by solving for this part. So let's do that. Here we got, so R equivalent is going to be 1 over 6 ohms plus 1 over 3 ohms plus 1 over 2 ohms. So let's do that. 1 over 6, 1 over 3, 1 over 2, add all that together, put it together, and R equivalent is equal to 1 ohms. So now we can rewrite this circuit, or redraw it, as 2 terminals with a 2 ohm resistor and now a 1 ohm resistor. So this part A, if you will, this is this. So now what do we do? Well, now we're going to take that, and it's clearly 2 resistors, and they are series. So we're going to come over here, and we can redraw this as just one resistor, REQ, is equal to 3 ohms, which is the 2 ohm plus the 1 ohm. So now we have another circuit. Now, I will admit there is a circuit in the homework that's going to cause you to maybe a little grief. It causes a few students a little bit of grief because it looks complicated because it's a 3-dimensional figure, but honestly, it's not many more complicated than this. What you need to do is pay attention to what's truly in parallel and what is truly in series. And sometimes these problems where they have a diagonal, it's really meant to just make you think. But in the end, it's only series resistance and parallel resistance. So a way you can always deal with this is you can always label the nodes. So if you ever get confused and kind of like, well, who's connected to what? Label everything the nodes, and anyone that's in a common pair of nodes, those are in parallel. And anything where the nodes are kind of joined together, you're going to add as in series. So we have node A. We'll just call this, we'll label that A. We're going to call this node B. Right? We can call this B. Technically, this and node C. We're just going to call that node C, because it's where everything joins together. And if you notice, we have R2 and R1, R3 and R4. So we have 4 total resistors. So let's see what's happening here. We have R1 clearly is in some sort of a parallel arrangement. It is in parallel with the whole thing because C is the output and it clearly is in parallel with everything. So we could redraw this simply like this, R1. So we have A and we have C. So as simple as that. So, and that's 10 ohms. Now, let's take a look what else we have. We have A going to B. So that's a resistor here. A going to B. and we're going to call this B here. And then we have two resistors that are both going to C, so this is clearly in parallel. So what I can do is this, redraw it like this, just so it's kind of obvious. And we end up with this being R2, this being R3, and this being R4. And putting the values with it, we have a 10 ohm resistor that's in parallel with an 8 ohm. That's then in series with the parallel of a 6 ohm and a 3 ohm. So let's break this down. So we know we'll start with this part first. We're going to start with this first here, and then we are going to then focus on turning that into a series, and then finally coming back and doing this. So 3 different analyses that we are going to do here. So the first one is the 6 and the 3. So using our little handy dandy equation we had a minute ago, we have 6 times 3 over 9. So this is 2 ohms. So we have now the circuit can be reduced as simply 2 ohm and this. So we have our two terminals A and C. Excuse my drawing here. I'm used to doing this on a whiteboard. So we have a 10 ohm resistor, we have an 8 ohm resistor, and now we have a 2 ohm resistor. So what do we have? We have this here, this 8 and 2 combined together, and we end up with A and C again. 10 ohm, that's in parallel with 10 ohm. Which is what? Well, just simply put, when you have two of the same thing in combination, so I have a 10 ohm and a 10 ohm in parallel, it is just simply 10 divided by 2. So if I have 5 and 5, it'd be 5 over 2. If it's 20, two 20s in parallel, it'll be 10 ohms, etc., etc., etc. So this immediately becomes one resistor that is 5 ohms. And that's the answer. For this slide here, we have two groups of parallel resistances that are in series. So let's take a look at that. We have this one here, and then we have this one here. So we're going to use the equation R1 times R2 over R1 plus R2 is equal to the equivalent for two parallel resistances, which on the first one, so we'll do the group for group 1 here, one ends up being 100 ohms times 50 ohms over 100 ohms plus 50 ohms, which is equal to 33 1/3 ohms. Now for the second one, using the exact same equation, we have 75 ohms times 25 ohms over, we end up with 100 ohms, which is 75, 25 over 100, and is 18.75 ohms. 75, 25 over, and then we just combine those together, because now that's two series, and the equation for series is R1 plus R2 is equal to R series, which means we end up with 33 1/3 ohms plus 18.75 ohms, which is equal to 6. Well, I must hit a button wrong there. Approximately, we're just going to say 52, and we had to 52.08333, and so on, repeating to infinity ohms. So now we have this circuit. We're going to do some different, now we have a little different thing. What are we looking for? This actually says circuit analysis. So like I said, this is going to be our first introduction to actually doing some real circuit analysis in this class. Next lecture, we actually dig more into what we call nodal methods using the Kirchhoff's current and voltage laws into truly coming up with a set of equations for the entire circuit. This is just going to be using what we just learned about combining all of these resistances together and do some very rudimentary circuit analysis. We're just simply using Ohm's law, and we're going to reduce the resistances down to one resistor and do like what we did at the very beginning of this lecture and end of the last lecture, where you just have a power supply and one resistor and you're solving for the current and or voltage, depending on what you're being asked for here. So let's take a look at what we have. We're given voltage. Our voltage is 90 volts, so we're told that. And we have three resistors. We have a 10 ohm that is in parallel with a 30, or a 10 ohm that is in series with a paralleled 30 and 60 ohms. So let's first reduce this. Let's first focus on that. So we have 30 and 60, which then becomes, this is simply equal to 20 ohms. So we end up with a 10 ohm and a 20 ohm resistor in series. So we end up with a circuit that the equivalent looks like this. 90 volts with, what is this, 10 and 20? So this is 30 ohms. And say you're being asked, what you're being asked for here is what is I? So what is I? What is the current? So I is equal to V over R. We know V and we now know R. So we can replace this with 90 volts over 30 ohms, which is equal to 3 amps. That's it. You just did your first circuit analysis. So this just highlights that for if you need to know how this is going on. So if you wanted to solve, and we're going to actually talk about what we call voltage and current dividers in a minute, but what we're doing here is we're showing that we have I1, which is actually what we're interested in this case, I1. And we've got a 10 ohm and we got the 30 and the 60. Technically, there are two currents, and this is the stuff we're really going to get to in the next lecture. He's dealing with these individual currents and writing equations for everything. Again, everything's going to come down to Ohm's law. And we just simplify everything by taking the combination of these three resistors, bringing it down into that, and then taking this and converting it into this. So you're going to have homework that's dealing with that. This brings us to the concept of voltage dividers. So we've been looking at a simple circuit, and we're now trying to figure out what can we use these resistor dividers that we have in, which can become a voltage divider. So we have here we have two resistors, R1 and R2. We have an input voltage, Vn, and Vn can be any voltage. And then we have V out, which is across R2. This voltage here. And that is governed simply by this equation. V out is Vn times R2 over R1 plus R2. So you might be asking yourself, where does this come from? How did we get this equation? Well, we used Ohm's law for this. So there's assuming that there is nothing out here. This is what we consider unloaded. V out is the voltage across R2 with nothing else connected to R2. That's very important. So it's just R1 and R2 is the only things in circuit, which means we have a current flowing through this entire circuit we're going to call is I, just simply I. So what can we say here? We know that I is equal V over R equivalent, right? And so V is equal to Vn, and R equivalent is R1 plus R2 because this is a series circuit. And you can already kind of see the shift here, right? Now let's ask ourselves, what is V out? Well, V out, using Ohm's law, and remember, V is equal to I R, meaning the current entering the positive node of the component, resistor in this case, times its resistance value. So I times R in this case. So V out is R2 times I. So if we now solve for this, we end up, and we now when we combine all this together, we want to know V out is equal to V in over R1 plus R2, right? So that's the I times R2, which leads us to this equation. So here we have three resistors. We have R1, R2, and R3. And we're now asking, what is the division of voltage across the three resistors? Now, a little fun fact here, V1 plus V2 plus V3 must equal V total. Remember Kirchhoff's voltage laws. And in a loop, there is a net sum of voltages must be equal to 0. So V total must equal V1 plus V2 plus V3. And if we use the same concept we just talked about, we have a current that's going through here, I, that must be maintained as well. There's no other currents that's going on in the circuit. It's just simply the current that is flowing from V1 to V2 and V3 back through V total, through the power supply. So it's as simple as that. So the equation, same process that we just went through a moment ago, we can now apply to this circuit. And what that works out to is the voltage number 1. In other words, the voltage that is across R1 here is the I times R1. And of course, as we just discussed a moment ago, the I is simply equal to Vn divided by R1 plus R2 plus R3, the equivalent series resistance, R1 plus R2 plus R3. So same thing we just did with the two resistor voltage divider applies to technically N number of resistors, as many as you want. In this case, it's 3. So you would take the sum, R1, R2, R3, and then you would multiply that by the component value that you are interested in this case, which is now, in this case, R1. So the Vn divided by this, basically, if you will, this part of the equation is the I, and then the R1 gives you V1. Correspondingly, V2 is IR2, or R2 divided by R1 plus R2 plus R3 times Vn. And in voltage number 3 is the same thing, Vn times R3 over R1 plus R2 over R3. So here's just a simple 4-element circuit analysis. And we are being asked here to determine what is V1 and what is V4. So let's do that. So let's do V1, and then we'll do V4. So using the math we just found, we know we first need to find the sum of the series resistors, and then we're going to multiply it. You're going to take, so we have that, and then we're going to, the equation is going to be 15 volts Vn times, in this case, R1, which is a kilo ohm, 1,000 ohms, over the series equivalent, which is 1,000 ohms, another 1,000 ohms, R2, R3 is 2,000 ohms, and 6,000 ohms, which just happens to be 10,000 ohms. So you have 1,000 over 10,000, or 1/10, times 15, which is 1.5 volts. So now let's do the exact same thing for the V4. So the bottom part stays exactly the same. So we got 15 volt and VN, 15 volts, but now we have 6,000 ohms over 10,000 ohms, which is equal to 15 over 6 over 10, which is equal to 9 volts. Current dividers. Same concept, just now we're going to be solving for voltage instead of current. So the question is, what is V? So current dividers divide the current in different branches depending upon the resistance values. So the current I total is flowing through that. So we know this. I total is equal to I1 plus I2. And this is because of Kirchhoff's current law, which we discussed the other day. So we know that. And we know that V is the same across both resistors. We have plus V across R1 and plus V across R2. So, well, we end up with this. I1 is simply V over R1, or I total, the total amount of current, divided by the, we have the R2 over R1 plus R2. So, because now we're in parallel. So we get this equivalence right here, R1 and R2, and we have that, and we multiply, and of course now, so what we have, so our equivalent, just so we can show the math of this, our equivalent, here, I'll do it down here because it's going to get replaced over, something going to write over it in a second. So our equivalent is R1, R2 over R1 plus R2. So we have that. And so what we're looking for is V over R1, right? So we end up with, V, which is, I R, or excuse me, the current is the voltage divided by the resistance. So you have V, excuse me. So V is equal to IR equivalent, right? Which is the I total times R1, R2, R1 plus R2. And then we're going to take that and we're going to multiply it or divide it by R1. And the R1s cancel out. And you end up with I total is equal to R2 over R1. Excuse me, R1 plus R2. That's how we get that. And correspondingly, I2 is just V over R2, which is the exact same thing, except now it's R2 that gets canceled out and not R1. So here we have a simple little problem to work. We have 3 resistors that are in parallel. They all happen to be 10 ohms. I'll let you work out the math on this, but the simple thing is if you have X number of resistors and they all happen to be the exact same resistance value, the easy way to do this is just to divide by the number of resistors. So in this case, I have 3 10 ohm resistors. The equivalent resistance is 10 divided by 3. So our equivalent is equal to 3 1/3 ohms. So V, so we can replace this circuit with this. And V is equal to 3 1/3 ohms times 3 amps. So V is equal to 10 volts. And of course, we get 3 amps from the power supply right here. So that's V. So now the question is, what is I1? I1 is just simply the V, 10 volts, divided by the resistance, 10 ohms, which just so happens to be 1 amp. And since they all happen to be the same thing, well, that's exactly what you would expect, 1 amp and I3. Which just so happens I1 plus I2 plus I3 is equal to I total. That's from KCL, Kirchhoff's current law, which just so happens 1 amp plus 1 amp plus 1 amp is equal to 3 amps. So in summary today, we talked about resistances in series, resistances in parallel. So in series, we add all the resistors together that are in series, and in parallel resistances, it's all about 1 over the reciprocal. So if you have 2 resistors though, the simple equation to remember is R1 times R2 over the sum of R1 plus R2. That equation is extremely useful to use. In fact, you can use that in multiple combinations of resistors, and eventually we're going to learn something called impedance later in the class, which is very much like resistance, and it's going to be the same thing as applicable there. So again, resistors in series, you add up, and in parallel, it's just 1 over the reciprocal. So 1 over R1 plus 1 over R2 plus 1 over R3 to a 1 plus, 1 over Rn, or N is the number of resistors that you have. Another trick as well to remember on parallel resistors, if you have X number of parallel resistors that are all the same value, then the equivalent resistance is equal to the resistance given divided by X, or N, the number of resistors you have. So if you have two 50 ohm resistors, then the equivalent resistance in parallel, if they're in parallel configuration, is 25 ohms. If you have 4 100 ohm resistors in parallel, then it's just 100 divided by 4, or 25 ohms. Then we talked about voltage and current dividers, using these resistances with a voltage source driving it, and therefore you're getting basically a proportion of the output voltage is equal to the total voltage coming in. So if Vn is 10 volts, and I've got R1, the output voltage is equal to Vn times R1 or R2, the resistor in question that is being analyzed over the sum of the resistances of a 2 element resistor divider or voltage divider circuit. You would have R2 over R1 plus R2 for the voltage across R2. If it's the voltage across R1, it would be R1 plus R1 over R1 plus R2. And then the same thing applies with current dividers, except now the resistances are in parallel with the current source, and the current is being divided through the resistances from the current source, from the total amount of current. And this is the same general rule applies. It's a proportion of the current based upon the total resistance and the individual resistances in nature. So again, this will be a good time if you have questions to attend the live Q&A sessions, where we do a quick summary of the lecture, go over any key points, discuss any homework problems that are causing anyone any problems, work on maybe a couple more problems that are a little more difficult, and really kind of explore some of the details of this lecture. So make sure you're attending that. Thank you and have a wonderful day.